We're jumping to section 1.4. We'll come back to 1.3. The properties of matter. So we identify substances by their properties and by their composition. So we have to talk about different kinds of properties. There are quantitative properties. These are measured and expressed with a number. So quantitative refers to a quantity. So there's lots of quantitative properties. Can anybody think of one? Like if I had a sack of potatoes, how might I describe that using a number? How much it weighs. So the weight of something. We could say, well, that weighs 10 pounds. That's a quantitative property of that bag of potatoes. How else could we describe the bag of potatoes?
How many there are?
How many potatoes? So you could count the number of something. Number, or how many. If you had, say, a cup of coffee, you could take the temperature of the coffee. Is it hot? Is it cold? What's the temperature? So that's another quantitative. Has to do with a number, okay? And then there are qualitative properties. That's referring to the quality of something, and this doesn't require an explicit measurement. So how could we describe the potatoes? Color. We say, well, they're brown. How else could we describe them? The shape. We could comment on whether they're clean or dirty, whether they're fresh or rotten. These are word descriptions. There's no numbers attached to that. And so throughout chemistry, we'll see that we have quantitative properties and qualitative properties. We need to understand what those two words mean. Any questions? We also have physical properties and chemical properties. I told you we like to classify things. So a physical property is a property that we can observe and or measure without changing what the substance is. We can measure it or identify it without changing the identity of the substance. So this may involve a physical change. So examples of physical properties. Let's see. This looks like an abandoned piece of paper. So here I have a piece of graph paper. What type of properties could we use to describe this? Dimensions. We could measure the dimensions, right? So we could say, well, this is 8.5 inches by 11 inches. So size. Length, width. We could weigh it, its mass, how heavy it is. Now, if I take this piece of paper and I tear it in half, a person got a 0 on that quiz anyway, right? Is it still paper? Yeah. Did I change the size of the paper? I did, but it's still paper. That was a physical change of tearing it in roughly half. Okay. Other physical changes are things like state changes. You take an ice cube and you let it melt on the counter. Did it change? Yeah. Is it still water? Yes. If I take water and I boil it so that it becomes steam, I'm changing the water, right? And I could measure the temperature at which that occurs. It happens at 100 degrees Celsius. So the temperature of it boiling would be a physical property. When I do that, when I observe that change, observe the property, I don't change what the substance is. So a boiling point would be a physical property. I could measure the density of something. density, color, there's lots and lots of physical properties. When I observe the physical property, it does not change what the substance is. What if I lit a match and burned this piece of paper? That would change it. It wouldn't be paper anymore, would it? We'd have some ashes and some smoke in the air, and we'd probably set off some sprinklers or something, who knows. That would change it. Does paper burn? Is burning a property of paper? Yes, it is. Paper does that. It's not a physical property, though. Okay? It's a chemical property. A chemical property is one that you cannot study or demonstrate without changing the substance into something else. So paper burning is an example of a chemical property. So paper burns. Generally, a chemical property is really a description of a chemical reaction that occurs. After you have a chemical reaction or a chemical change, the original substance is destroyed and new substances are formed. If I take an egg, a raw egg, and I crack it into a hot skillet, what happens to the egg? It cooks, right? It goes from a liquidy, gelatinous thing into a more solid thing. The color changes. The texture changes. Is that a chemical change or a physical change? So that's a hard thing to think about, isn't it? It's actually a chemical change. It's a chemical property that when you heat an egg, what's happening is that the proteins in it are denaturing and changing, and that's not something that can just go back to how it was before. That egg is permanently changed by the addition of the heat. If you take an ice cube and you heat it up, it changes, right? It melts, but it's still water. The individual particles are still the same. Okay, you take natural gas and you light the fire, you light the burner to make the flame to cook the egg. The gas is burning. Is that a chemical change or a physical change? It's a chemical change. The gas is turning into something else. Now, when you're very first getting started in chemistry, it can be a little confusing as to which one is chemical and which one is physical. So paper burns, hydrogen, well, I already talked about hydrogen. Let's see, TNT, trinitrotoluene. It's a mouthful. That's why we call it TNT. Is it explosive? Yeah, TNT explodes. That's a chemical property of TNT. When you demonstrate that chemical property, you don't have TNT anymore. When I demonstrate the length of this piece of paper, I still have paper at the end. Even if I demonstrate the property that I can tear paper into smaller pieces with my bare hands, it's still paper. So, taking a piece of wood and an axe and chopping it in half, it's still wood, right? It's just two smaller pieces now. That's a physical change. If I put the wood in the fireplace and burn it, it's not wood anymore, and that's a chemical property, a chemical change that wood burns. Any questions?
So does it all have to have fire or something?
It does not always have to have fire. Fire is just the most convenient, most understandable chemical reaction. Okay, so the Alka-Seltzer. You drop Alka-Seltzer in water and it forms bubbles, right? That's a chemical change. The substance that was in the Alka-Seltzer is undergoing a chemical reaction and it's forming carbon dioxide bubbles that then bubble up through the water. And so what you have at the end is not the same substance that you had at the beginning. You mix baking soda and vinegar together. It's something you can try at home. It'll bubble and fizz. It's making carbon dioxide gas. That's what happens when you're baking cookies. The carbon dioxide generated by the baking soda causes the cookies to puff up a little bit. It's a chemical change. Okay? More properties. Extensive and intensive. Okay, so here we have prefixes again. Ex and in. What does it mean to exit? We don't have an exit sign in here. I guess we can figure out where the doors are. Usually there's an exit sign over the door, right? When you exit, what do? You go out. Ex or exo refers to out. In refers to in, right? So an intensive property is like an intrinsic quality. It pertains to the substance itself. It doesn't matter what's going on outside. So an extensive property does depend on external factors in a way. It depends on how much matter you have. Do I have a full sheet of paper or do I have a quarter sheet of paper? Well, here's a full sheet and here's a quarter sheet. Which one, do they have the same mass? Does this little piece have the same mass as the big piece? No. The mass is different because I have more paper in the larger piece and less paper in the smaller piece. Mass is an extensive property. How about the length of this piece of paper? This full sheet and the quarter sheet. Is the length different? Yeah. It depends on the amount of substance. So the mass, the length. What about the color of the paper? Those two pieces of paper, they're the same color, aren't they? That doesn't depend on how much of it I have. The color is an intensive property. I can take this piece and tear it in half. I'm having fun tearing up paper today. The color didn't change. So the intensive property there would be the color. So the color is intensive. The size is extensive. What about density? Actually, let's go. The density will be the same. And we will talk a lot more about density. Density is the mass of something, how heavy it is, divided by the volume that it takes up. You've heard that joke, which weighs more, a pound of feathers or a pound of bricks? They both weigh a pound. Yeah. Why does that mess up our brains? Which takes up more space, a pound of bricks or a pound of feathers? Feathers. Why? Because feathers are fluffy, right? Feathers are less dense. For the same amount of mass, they occupy a greater volume, right? So if I have a brick that has a particular density, and then I cut the brick in half, well, I've changed the mass by half. I've also changed the volume by half. The density doesn't change. The density of something does not depend on how much of it you have, because it's a ratio of mass to volume, and they both change in the same way. How about temperature? If I have a cup of boiling water, or I have a big Dutch oven full of boiling water, different amounts of water, does the temperature change because I have different amounts? If it's boiling, the temperatures are the same. So temperature is an intensive property. It doesn't depend on the amount of stuff. Any questions? Okay, here's a sample problem. The diagram shows a compound. We're looking at diagram A. The diagram shows a compound made up of atoms of two elements. So we've got the green ones and the red ones. And so each of these little molecules is one red and one green. This is in the liquid form, and so we see that they're just kind of plopped all over each other, but they're close together. This is asking which of the diagrams in B to D, so which of these three, represents a physical change. So in a physical change, are these individual pieces going to change? No. The individual components are the same. A physical change doesn't change the identity of the substance. Well, is this one changed? Yeah, now we've got two greens and two reds. So that can't be a physical change. How about this one? We've got the same particles, but they're not attached to each other anymore. Over here, we have these same particles that we had over here. One red, one green. One red, one green. They're all the same. What's changed about them? They're spaced out more. Okay, so that is a physical change. The individual particles didn't change. That's a very important thing about a physical change. The particles themselves don't change. That's a physical change. So this one's a physical change. And thinking in terms of states of matter, if this is a liquid, then what's this one? A gas. So that's turned into a gas. So you take water and you vaporize it, it's still water molecules. Those haven't changed, but now the molecules are separated from each other. And then it asks which diagram represents a chemical change. Well, we said this one's physical, so now we just got these two left. A chemical change, the individual particles are changing. So here we had little diatomic molecules of one red, one green. What do we have here? We have two reds or two greens. Is that a change in the particles? Yeah. Is that a chemical change? Yeah, that's a chemical change. So that's a chemical change. How about C? Is C a chemical change? Yeah. This is different than that. The individual particles are different. If we're talking about Legos, here we took these little structures apart and we just recombined the blocks in different ways. And over here, we took them apart entirely. So these are both chemical changes from A. Would this be a gas, a liquid, or a solid? A gas. And how about this one? It would also be a gas, because there's space between the particles. Any questions?